Hello everyone and welcome to Speeding Up MATLAB Applications. I'm Vipresh Gangwal and I'm part of MATLAB Math team at MathWorks. Today we are going to discuss how you can improve performance of your MATLAB applications. These techniques will allow you to use MATLAB efficiently and increase your productivity. Specifically, we are going to look into how you can make full use of MATLAB's matrix and vector operation capabilities. We'll then see how you can use MATLAB Profiler to find bottlenecks in your code and address those bottlenecks. This will allow you to narrow down the parts of your code where you need to invest time and efforts for optimization. Once we are able to get a good performance by running MATLAB in serial fashion, we'll see how we can use additional compute power for your application by using MATLAB's parallel computing tools. We'll also briefly talk about integrating languages such as C and Fortran into MATLAB to improve performance. Okay, so MATLAB stands for Matrix Laboratory. MATLAB is really good in dealing with matrices and vectors. Let us see how we can use this for our own advantage. So I would like to begin with showing you an example that will allow you to take full use of matrix and vector operations. For most of the examples today, I'll start with working on a script or a function that is completely functional. And I'll act as if I have gotten this function from one of my colleagues, one of my coworkers, and my job is to optimize it. In this way, I'll be able to walk you through the process of how I analyze and speed up code's performance. Specifically in this first example, the code I have evaluates an expression over a grid of xy values to compute an image, and then re-evaluates an averaged image by taking average of the original values on blocks of a given size. In the end, it compares these two results visually, and we are going to evaluate the code performance for this particular function and see how we can optimize it. So let's go over to MATLAB and look at the original code. I'm using our 2014A release of MATLAB. So I have this block avg function here, and I want to time this. I want to see how much time does it take for this function to do its computation. So I'm going to use tick and talk function. I have a tick here at line 12, and if I scroll down at around line 64 is my talk. So I've kept the plotting part out of it, but I'm timing the computation, all the computation that is going on. So if I try block avg of, let's say my image is of size 2000 by 2000, and I'm taking block average over a block size of 20 by 20. Let's see how much time it takes. So tick talk function will calculate the time elapsed between tick and talk calls, and it will display it on command prompt by default. Now the computation is done. I can see the images, I can compare them. I'm more interested in the elapsed time, the time it took for this computation. And it took around 7.05 seconds. Now, by the time we are done with playing with this function, by the time we are done optimizing this function, we'll improve its performance, and let us see how much can we improve this performance. So I have a redo 2 version, which is after a few steps of performance optimization. But for this final code, if I give the same input parameters, I should expect the same output, and I get the same output, but almost instantaneously. The execution time has come down to 0.19 seconds, where we begin from 7.0 seconds. So if this kind of speed up excites you, I would encourage you to stick around for this webinar and learn different techniques on how to optimize your own performance for your applications. Okay, so let us switch back to our block avg code and see what is going on in here. In this code, we have this first section where some parameters are being initialized. And if we scroll down, we have setting up values for surface on the grid. So this is the initial image being calculated. You can see a nested for loop is used here. This is typical and natural programming style for a lot of people who program a lot in C and Fortran, But in MATLAB, there are efficient ways to do this, and we'll jump to that in a few minutes. Let's continue to see what else is going on in this function. We have another set of nested for loops with an if statement to calculate the averages over a block. And then in the end, we have the plotting going on. Okay, so in order to optimize this code, the first step that we can take, the first step that I would encourage you to take, is to take help of code analyzer. Code analyzer is this square block on your right hand side. That's the way code analyzer communicates with you, and you can see a red, an orange, or a green square there. Code Analyzer is MATLAB's static code analyzer, which looks into your code, which looks into the file which is open in MATLAB editor, and suggests if there is something wrong with it, if there are some recommendations in it. So a green color would say everything's fine, go ahead and run it. A red box would say, uh-oh, wait, check, there is something seriously wrong. Maybe there's going to be an error when you run this code. We have an orange box, which means the code will be able to run, but there are some things which we can improve. So what are the things we can improve? We can find out by hovering over or clicking on these lines. When I click on that line, it brings to that piece of code where that warning appears. And by placing my cursor there, I can see MATLAB Code Analyzer is telling me that the variable mySurf appears to change size on every loop iteration, and consider pre-allocating for speed. So what MATLAB Code Analyzer is telling me is, because of dynamically changing the size of mySurf in every iteration, I may be seeing some performance being hindered here. And to get a better performance, I should pre-allocate. I have a couple of options to pre-allocate. I can use zeros or ones and functions like these to create a matrix beforehand of the size of mySurf, and then just replace those values as and when we go. So that is pre-allocation. And that's what is being suggested. But let us see what all other suggestions are there for this code. So we can see, I see there are other warnings in here. I can click on each one of those and figure out what the warnings are, or I can use check code function in MATLAB and pass the argument as the file name which I want to analyze, and it will check the code in that file, give me a list of all the warnings and errors, and give me hyperlinks to those lines in the code. As it turns out, all the warnings that I am getting for this particular function are about pre-allocation. So if I pre-allocate these 4 variables, I should see some performance improvement. How much of a performance improvement? Let us find out. So I have this block average redo 1 file, which is the first redo, the first improvement. And let me just compare both of these side by side and see what's going on. So the first thing I can see is, well, the code analyzer is turned green. So I have somehow taken care of all the warnings. And what I've simply done is, before using any variable, I have used zeros function to create a matrix of this final size and fill it up with zeros. That way I've gotten rid of the warnings. I have pre-allocated these arrays. Later on we'll look into how pre-allocation helps in speed up. But right now, let's just run this file and see how much of a speed up did we get? How much of the time saving is there in pre-allocation? So I can say block average redo 1 and then pass it the same input arguments that I have been using and see what is the time it requires to execute. Wow, it just took 0.7 seconds. So from 7.1 seconds to 0.7 seconds, that is a good speed up. And all I had to do was add those 4 lines of pre-allocation. So pre-allocation is a pretty good way of getting speed up, and your code analyzer warnings a lot of times will be around pre-allocation. So if you're missing out on pre-allocation, doing that as a low-hanging fruit will give you good speed up. All right, so now I have pre-allocated and I have this block average redo 1. What else can I do? How can I improve it further? Other than pre-allocation, I can do vectorization. And vectorization is a way in MATLAB, vectorization is the practice in MATLAB which deals with replacing your for loops, replacing your while loops, replacing your scalar operations with matrix and vector operations so that MATLAB can run them more efficiently. So in this case, going back to the nested for loop that we were talking about, in MATLAB, I can do this whole operation. I can generate this whole image by using matrix based equations instead of iterating over each element of my grid. So the first step I need to do is create a grid and then use that grid as an argument to my cos and sine functions to generate my surface. In order to create this grid, I can use a function called mesh grid. So if I type mesh grid in the help search, I can see the help documentation for the function mesh grid. And as you can see from the example, what mesh grid does is it takes an input of two vectors, say x and y, and it creates these matrices which are combination of all possible values of x and y. So it gives me this grid, and then I can use that grid to calculate the value of a surface over that grid. There are other examples which show that. So another function to do this in n dimension is ndgrid, and so on. So what I'll do is I'll use mesh grid instead of this nested for loop to create my x and y values and then pass it to my surf to see if my redo to function shows that change. And again, a left and right comparison will show that instead of pre-allocating and having a nested for loop, all I need to do is use mesh grid to create x and y grid and then pass it on into my cos and sine functions into the same expression. This is smaller, 2 lines code, cleaner and easier to read, but more importantly, it is going to give me performance improvement. Now there are other functions such as mesh grid that I can use for vectorization. And what if I don't know about them? What if I don't know about mesh grid as well? One of the good ways to find functions which can help you in vectorization or in general learn about vectorization is to search vectorization or vectorizing in your documentation search. And if you go to this concepts page for vectorization, you will see there are a lot of examples in there. Specifically, if I jump over to matrix operations and scroll down a little, I will see a list of commonly used functions in vectorizing. I can see my favorite mesh grid and ND grid in here, but there are other functions such as reshape in here. So I can use these functions to take my code and vectorize it. In fact, I can use reshape in my second nested for loop to actually compute the block average. So let us see how I have done that. If I scroll down this code, I have this huge nested double for loop, and instead I can add these lines here. Now I have created these x and y positions, and then I have reshaped, summed, and then reshaped again. So this may not be so intuitive. Sometimes vectorizing makes the code more readable. Sometimes it takes away the readability of the code. So it's a compromise that you have to make, and you make the decision. But almost always vectorizing your code will give you better performance. So from redo 1 to redo 2, let us see what is the speed up. We actually have executed redo 2, and we know it takes 0.19 seconds. So we started from 7.05 seconds, and just by pre-allocation, just by making sure we have pre-allocated all the matrices which are changing sizes, we got time down to 0.7 seconds. And then by vectorizing our code, we got that final improvement in time and reached 0.19 seconds. So to summarize this example, we started with this tick-tock function and timed our example, but we relied on the code analyzer to suggest us how to improve our code initially. And what code analyzer gave us is pre-allocation. Pre-allocation helped us improve a lot in our performance. Let us see why. Let us look into how pre-allocation actually assists, how actually it makes sure that performance is better. So if I'm not pre-allocating memory, what happens? If I want to say x equals 4, MATLAB finds a memory to hold one number and puts 4 in there. Now if I want to add another element, MATLAB has to find contiguous space because MATLAB stores variables in contiguous space. If it cannot find any neighboring space near 4, it will find a space of size 2 somewhere else, move 4 there, write 7 and then erase 4. And as the size of matrix increases, you can imagine these memory read-write operations, the memory move operations will become more and more expensive, will take more and more time. So resizing arrays is expensive and you should avoid it as much as you can. Instead, if you pre-allocate, say by using zeros of 3 by 1 in the previous example, MATLAB will find a space big enough to store 3 numbers. And now whenever you are assigning number to any particular index, all MATLAB has to do is go and replace that memory location. So you have reduced number of memory IO operations when you are using pre-allocation. So because of these reduced memory operations, you get that performance benefit. Now MATLAB implements some smarter techniques to make sure that you don't get such a big performance hit because of dynamically changing size of your arrays. But if you have really big arrays, all you want to do is actually pre-allocate, and that will ensure that you get best performance. On the other hand, we also talked about vectorization. And vectorization is good. We saw it increases or reduces readability, but it also impacts memory. Vectorization almost always gives you better performance, but you have to consider its impact on the memory usage because you're creating all these extra matrices. And if you have really big data sets, that may impact on how you are dealing with your data and how you're running out of memory. One of the ways to deal with that is using BSX-fun, which is binary singleton expansion function. But another really interesting way is to use best of both worlds. So you use a for loop, but inside a for loop, instead of iterating over each element, you divide your bigger matrix into blocks and do matrix operations on the blocks. So each of these blocks are vectorized, but you are still creating smaller matrices and not running out of memory. Another thing that you can do to take care of memory is using sparse matrices. So if you have a lot of zero elements in your matrices, using sparse matrices will save memory for you and also give you better performance because you will have lesser number of calculations going on. Let's talk about how data storage happens in MATLAB, how MATLAB stores its arrays, and how we can leverage that to improve performance. Can we use that in some way to take care of our performance? So if we have this array X, which is a magic of 3, we know MATLAB will try to find the space big enough to hold 9 numbers, and it will start saving 8 on the top. But what next? Does it save 3 or 1? As it turns out, MATLAB saves 3 and then 4 and so on. So MATLAB is column major. MATLAB will read down the first column and then the second column and so on to save these numbers. How is this useful? Well, if you're not vectorizing your code and iterating over elements, you want to iterate over columns instead of rows. You want to go column wise instead of row wise, and this will make sure you have better memory caching and give you a better performance. Another thing is indexing into arrays. So we know how arrays are stored. But when we are fetching value, when we are accessing those arrays, when we are accessing those values, can we do something differently to get better performance? So there are 3 ways in which you can index MATLAB arrays. One of them is subscripted, very popular. We all know you can use the row number and the column number to index into a 2D matrix, and you can access that element. But there's another way of indexing into an array, which is called linear indexing, where you use a single number, and this number is calculated by counting down the columns. So linear indexing is faster than subscripted indexing because of the way MATLAB stores its numbers. And if you can, you should use linear indexing instead of subscripted indexing. MATLAB actually provides you these 2 functions to convert between the 2 indexing types. A third type of indexing is called logical indexing, where you can use a logical mask to index into a matrix. Let me illustrate to you what do I mean by logical mask. So if I clear out everything from screen, let me create a vector of size 8 having 8 random integers. Wow. So I did a typo in there and MATLAB gave me did you mean a recommendation on spelling and the correct function. Now I have X here which has these 8 elements, and if I want to access all the elements which are greater than 5, I can create a logical mask IDX where X is greater than 5, which gives me a 1 wherever X is greater than 5 and 0 everywhere else. So it's a true and false vector. And I can use this vector to index into X and fetch all the values which are greater than 5. So you can see all my values which are greater than 5 are being displayed here. I can actually say X of X greater than 5, and that will also return me those values. So I can start with X and I can use logical indexing to get all the elements which satisfy a certain condition. How is this helpful? Well, let's look at an example. So I have this magic of n, but here n is size 2000, so I have really big matrices A1, A2 and A3 which are of size 2000 by 2000, and I have a reference value of 10 to the power 6. So let me minimize this and go ahead. So if I use a nested for loop and iterate over each element and then compare that element with my reference, if that element is greater than reference, I'll store it inside my vals. If I use this approach, which is a pretty common approach, it takes around 0.13 seconds to get all the values. But let's see what happens if I use logical matrices. So I can use A2 of A2 greater than myref, like I used Ix of X greater than 5, and if I run this section, it takes only 0.05 seconds. So from 0.13 seconds to 0.05 seconds, you can see as your matrix gets larger and larger, you will get a good benefit out of using logical indexing instead of using subscripted indexing and iterating over each element. Well, that actually makes your code look prettier as well. It's easier to read and you understand what's going into vals. Another way of approaching this problem is using find function, and a lot of people ask me the difference between these two. Now what find function does is it finds the indexes of the places where a certain logical condition is true. So for example, if I save the output of find function in a variable, my index, you can see my index has these numbers 1, 4, 5. These are the places where A3 was greater than myref. So this is the linear indexing that we were seeing. These are the linear indexes of those places. So when I'm using find, I'm finding those linear indexes and then indexing into A3. And as I said, linear indexing is faster than subscripted indexing. So this is faster than the nested for loop, but it is not as fast as logical indexing. So for this particular example, we saw that logical indexing is faster than using find, and using find and logical indexing, both of them are way more faster than using a subscripted indexing and a nested for loop to iterate over each element. So simply by changing the way you are indexing into an array, you can get better performance. All right, so why is MATLAB so good in dealing with matrices? Why does vectorization give me so much value, and why do I need to pre-allocate? Why do I need those contiguous spaces? The answers to all these questions comes from the fact that we use commercial libraries such as BLAS and LAPACK under the hood to get you subroutines which are optimized for your programs, which are optimized for your operations. And the requirement of these subroutines, the requirement of these libraries is that those matrices be saved in contiguous memory spaces. But the advantage is it gives you these multi-threaded optimized code which makes your math operations run faster, which makes your matrix operations run faster. So what about the operations which are not optimized by BLAS and LAPACK? What about my loops? What about some other ways in which MATLAB is helping you to get a better performance? And MATLAB has another way. There is a just-in-time compiler or JIT accelerator. And what that does is For example, in case of looping, it creates this on-the-fly multi-threaded code for all the code within your loop if it can, to improve your looping. And every release we put a lot of effort in JIT to make it better and better. So one of the places where its effect has been notable is the performance of for loops has become better and better over multiple releases. So in summary, in this first part, we saw that using techniques such as vectorization and pre-allocation, you can get better performance. And while you are doing these, you can also keep in mind other considerations such as whether you should use logical indexing or subscript indexing, whether you are looping or you are doing matrix operations, and you can make these trade-offs and select the correct techniques, correct approaches to get better performance. But now the question is, where do you put those efforts? If you have a really big code, say 10,000 line, 15,000 lines codes, such huge code bases, where do you put your efforts on applying these techniques? How will you get best outcome of your efforts? And that's where addressing bottlenecks turns out to be very useful. You have to identify your bottlenecks. You have to identify the portion of your code which is taking most time to execute, which is slowing down your code, which is slowing down your application, and you have to address that. You have to put your efforts in there. So we are going to look into how you can use MATLAB Profiler to do that. The example that I'm going to use is another example where again I have a given code, and what this code does is it loads data from multiple files. It extracts one specific test from those data files. So these data files are in a format where there are multiple test results put one after the other, and there are almost 100 test results in each data file. I have data files from multiple plants. And what I want to do is extract one specific test from each file and then fit a spline to each of those data series and then write the consolidated results into Excel file. Let us see in MATLAB what I mean by all this. So if I switch over my demo to test fit, actually let me show you how one of those files look like. And here it is. So these are the text files that I'm going to deal with. It has the test result for the first test, and if I jump 499 steps, I should see the test results for the second test, and so on. There are 100 tests in there, and I have 10 such files. So how can I use this? Well, I have this code test fit, which was given to me, and what this code does is it reads in the files, it iterates over each file, reads in relevant model data, then for the desired tests it filters and fits and evaluates the spline. So it's doing the math operation, some pre-processing and fitting of data, and then plotting the results, saving it as an image file, and then putting overall results into an Excel file. So that's the code that has been given to me, and I want to find where should I put my efforts, which part of these, which section, which part of this approach should I focus my efforts for optimization on. I can throw a lot of TikToks here and there to see each block of code, how much time it is taking, but there is a better way to do that. There's a better way to find the bottlenecks, and that is to use MATLAB Profiler. So if I use the run and time button in my MATLAB editor tool strip on top, what it does is it'll run my default run option and it'll profile it. So it will see what functions take how much time, what sub functions are being called how many times, what are their timings. So it'll give me a relative timing between the function itself and its sub functions, and it gives me this overall summary here, where it took me around 8.8 seconds to do this test fit. And if I dig deeper into test fit, I will see that it has used, for example, it gives me the topmost or the worst lines, the lines which have taken most timing on the top. So these are the 5 lines of codes which have taken most time. And then if I can click on these, it will actually direct me there. So in the code, I can see these are color coded. So XLSWrite is dark in color, which means it's taking most time. All right. So this is my profiler summary. It is a result. It's giving me what is going on where. And how can I use this? Well, I know XLS write is the thing which is taking most time. Can I do something about it? Can I improve the performance by taking care of that particular line? Is the question that I want to ask myself. So XLS write is being called 10 times. And the job of XLS write here was to write the consolidated results into one Excel file. So why is it being called 10 times? If I go over to that line number, I can see it's being called before the end of the for loop. It's being called inside the for loop. It's being called for each individual plant again and again. So we are writing into the same file again and again, but we are opening the file. XLS write has this overhead of opening the file, connecting with Excel, putting the data in, closing the file, and we don't want to do that. So an alternative is I can replace this XLS write. I can put it outside of my for loop, and within the for loop I can just collect the results into a variable, keep collecting them, and then once I have all the results, I'll put them into an Excel file. Let us see if that approach helps, if I can bring down the time. So let me click here and keep these results for reference aside, and I'll minimize this. I'll show you the difference between test fit and test fit redo 1. So redo 1 is the place where I have taken care of the first bottleneck, the XLS read. Now to compare these two files again, I could open them side by side in MATLAB editor, but these are longer codes. These are codes with multiple lines, hundreds of lines. So an easier way to compare these two is if I select both of them in my current folder browser, I can say compare selected files and folders. And this opens up the MATLAB comparison tool, which shows me what are the differences. So I can see the name is different, and I have pre-allocated for XLS data some variable in my redo 1 version. All the computation remains the same, and I'm saving the results from spline time and data into this XLS data variable that I had created. Now another thing that has changed is whatever XLS write that I had inside the for loop is missing in my redo 1, and I have one single call to XLS write outside my for loop with XLS data being written. So I've moved the XLS write from inside the for loop to outside the for loop, and let us see how much of an improvement does that give me. So I can go to my profiler and say test fit redo 1 and pass in the inputs saying I want 60th test and 200 is the size of my splines. So if I run this, you can see it's being going a little faster than what it was, and in fact I can see that it took 5.6 seconds in comparison to the original 8.8 seconds. So just by changing that XLS write, my profile has changed. Now XLS write is not my worst function. It's being called only once and it's taking lesser time. Great. So I have come from 8.8 to 5.6 seconds, and if that is the performance I'm happy with, I can go ahead and I can say I've optimized the code. But if I want to optimize further, if I want to go ahead and put some more efforts and get some more performance out of this, get some better speed out of this, I can continue the exercise of focusing on bottlenecks based on these top functions, functions which are taking most time. So now the function which is taking most time is text scan, and it's being called 590 times. That is just sounding wrong. Why would I scan something 590 times? Let me look into it. And here is the text scan. If I scroll up, I'm not even saving the output of text scan. I'm just iterating over text scan so that I can get rid of all the undesired tests. So if I want to jump to 60th test, I'm doing 59 iterations of text scan just to dump that data for 10 different files. 590 useless text scans doesn't make sense. So I can open up the documentation for text scan, and once I do that, I'll figure out there is a better way to call this function. By changing the arguments that I'm passing to this text scan, I can actually call it only once instead of calling it inside the loop. Another thing that I can see here, which is taking time is the save as and the figure functions. So I'm creating these 10 figures and I'm saving them in figure files. Now these are 10 different files, so I cannot change save as. I have to save 10 figure files. But can I not call the figure function? What's happening when I'm calling figure function is I'm spawning these new figure windows and I'm plotting in them instead of reusing an existing figure window. If I remove the call to the figure function, I can reuse an existing window. I can keep plotting new data in that by removing old data, and I don't have to pay the overhead of creating a new figure. And if I have some extra labels and other customizations, I can save those customizations. All I need to do is change data, and I don't need to spend time in those customizations as well. So I can remove the command figure and see how that affects the performance. So I'm going to make these two changes. So from test fit redo 1 to redo 3, let's jump 2 steps and see what is the effect of these two changes and how those two changes look like. Again, the code looks almost similar. The few lines of code that I've changed are text scan, instead of being called inside a for loop, is now being called a single line, and I've changed the arguments being passed. Another change is the figure call to figure is missing. We have just removed it. And instead we have added a call to draw now just before we save the figure, just to make sure that the figure is updated with the latest data. Okay, so with this in mind, let's see how much time does it take for my profiler to run test fit redo 3. And if I run in time this, oh my god, you can see how fast those figures updated. And in fact, it took only 1.7 seconds. So that is a speed up that we got by reusing the figure windows that we had and by using text scan, the function, in a correct form, in the correct syntax. So if we look at this example, we used Profiler to analyze our code, and we targeted significant bottlenecks where we could put our effort and get most speed up. We reduced the file IO, the file input output operations, and we reused figure windows. So we reused whatever figures we had generated. As far as analyzing the performance of a code goes, we saw how you can use Profiler, how it gives you bottlenecks. We also saw how you can use tick-tock functions to time a section of code like a stopwatch, and it just displays you that code. It's easy and handy to do timing for some scripts while you're developing. Another thing which you can keep handy is the time_it function, which allows you to time small running time functions that you have. It runs those functions multiple times and computes the median computing time for your functions. So you can use any of these to analyze your performance, and you can find bottlenecks. So while using Profiler results, you can focus on the top bottlenecks which are listed on top, which are these functions which are taking most time. And an important thing to take into account is not only how much time per function call it's taking, but how many times the function is being called. If you remember, in case of text scan, it was being called 590 times. That was a lot. We could change it. And then each function call actually has an overhead. So you don't want to call a function a lot of times. All right. What about MATLAB functions? We saw text scan or text read can be used in different ways. There are different input arguments, and both of these functions do sort of similar stuff, but both of them have different performance for different kinds of inputs. So finding the right MATLAB function is an important thing to do to get your performance right, and it is not as easy as it sounds, because all these MATLAB functions, there's so many different ways of using it. It's so much flexible. So I encourage you to read the documentation pages to figure out which function suits you the best in order to get better and better performance. A lot of MATLAB functions actually have viewable source code. So by typing edit space the function name in MATLAB command prompt, you can see the source code. And by looking at this, you can write your own functions to do similar stuff, where you can ignore all the extra error checking or extra outputs that are being created that you're not using. So you can write your own custom functions to do similar stuff, which can have better performance. So in terms of bottlenecks, we already saw that file IO is expensive and you want to reduce it because obviously disk is slow as compared to RAM. We saw displaying output is expensive. In our case, reusing figure window helped. In a lot of cases, we have a printf statements or displaying the variables of displaying the values of variables on command prompt, and this is unhealthy. This causes a lot of time being spent on displaying that output. So if you have intermediate outputs being displayed that you wanted to display while you were developing your code, that's fine. But once you are done developing your algorithms, you can start skipping those. So after addressing these bottlenecks, another type of bottleneck is computationally intensive functions. These are functions where the function is taking a lot of time. It just has a lot of calculations. You have done all the memory IO right, you have used all the techniques, you've done pre-allocation, but there are a lot of functions, there are a lot of calculations happening. What do you do in those cases? So you can use additional hardware, or you can use other languages and integrate that in MATLAB. So MATLAB has this MEX interface or MATLAB executable interface, which allows you to bring C or Fortran code directly into MATLAB. So you can call these C or Fortran functions from MATLAB. And this will help you to optimize the performance in some cases when your for loop is state based. So each following iteration of for loop is dependent on the previous loop. Sometimes this may give you some speed up. Now, if you don't have these C functions, you can use MATLAB coder product to generate C functions out of your MATLAB functions and then mix them. A point to note is this may not always be helpful because a lot of MATLAB functions are already multi-threaded. They are already using BLAS. They are using mathematics libraries. So if you try to mix those functions, if you try to convert those functions into mix functions, you may not see that speed up. But in general, accelerating using mix is one of the options that you can keep in mind. Another option is to use more hardware. And before you jump to using more hardware, before you jump to use your GPU, your multi-core CPUs, I would recommend you first focus on getting your code working right, getting the right results out of it, and then focus on getting best speed in the serial fashion, in your serial MATLAB, in your normal MATLAB window. Once you have that performance, now if you jump to additional hardware, you will get best out of the additional hardware as well. So your optimization will be easier if your code is already optimized to work on a serial MATLAB session. So now let's jump to using that additional compute power, using those GPUs or using those CPUs with multiprocessors and multi-cores, or using cloud and cluster to increase your compute power, and how we can do that in MATLAB. Now there are two ways of using additional processing power. There is built-in multi-threading where MATLAB directly is exploiting all the available cores to do some math operations, and this is by default available to you. Since R2008A, MATLAB by default does this. You don't have to worry about it. The other way to do that is using parallel computing tools that we provide, which gives you some high-level constructs that you can use to write your own parallel code. And this is where I'm going to focus the rest of my seminar today. So parallel computing toolbox is one of the tools that I'm going to use for demos in parallel computing. And what parallel computing toolbox does is enables me to communicate with MATLAB workers. These are headless MATLABs running on my machine, which help me to exploit all the cores on my machine. If I want to exploit distributed computing, for example, clouds and servers and grids, I can use MATLAB distributed computing server and use the same constructs that I use on my local machine to scale this application onto a cloud or a cluster. So we're going to focus on how to use parallel computing toolbox today. And let's jump right into this example, which is a very popular parallel computing example. Very common type of an application which people do is parameter sweep. So what is a parameter sweep is we have these parameters B and K for this example, and we want to simulate the system, we want to compute the output for different values of B and K, different combinations of values of B and K, and then record the peak value for each run, plot it. So I have this second order ODE and I'm going to use it. Now such problems are really good to be use with parallel computing because these are embarrassingly parallel. Each iteration is independent of each other, and that's why they give very good results while using parallel computing. So let me jump into an example and let me show you the script. So this script is what we are going to work with. This is again a pre-written program that I've gotten, which starts with initializing the problem and initializing my k and b values. It then uses mesh grid to create that grid, and then I have this big for loop, the main part of my function, where it is using ODE45, an ordinary differential equation solver available in MATLAB, to simulate the system and get the peak values. So I'm timing this. Let me run this as it is and see how much time does it take. So right now MATLAB is using the ODE45 solver, which is a numerical solver, and solving around 3,500 differential equations. That is a lot of math to do. So MATLAB is crunching these numbers, is looking at these numbers, and it should take around half a minute. Oh, there it is. So in 19.9 seconds, MATLAB was able to solve 3,500 differential equations. That's great. MATLAB is already fast, right? But what if I wanted to make it faster? What if my system has a lot of different parameters that I want to simulate? Can I do something? Can I use multiple cores? Can I make use of parallel computing? And yes, I can. So my first step to do that is to create that pool of MATLAB workers that we were talking about. And if I take my mouse to the left hand lower corner of my MATLAB window, I can start a parallel pool by clicking there. So when I ask MATLAB to start a parallel pool, it is creating these headless workers, and I will have access to using them as soon as it's ready. So I have connected to 4 workers. That's because I have 4 cores here. You can create as many workers, as many cores you have, so you can make full use of your computer. Now, the next step is to let MATLAB know that I want this for loop to be evaluated in parallel. I know these iterations are independent of each other, and why don't you use the workers to calculate this? To do that, I have to convert the for loop to a parallel for loop by adding 3 letters in front of my for loop. That's it. PAR for, par for. That's the only change that I do to my original code. And if I run this now, the same parameter sweep should take lesser time and give me results. So I got the parameter sweep done. I got it done in 5.04 seconds. Right? So I can see I can get these results within 5.04 seconds, which is a pretty good time, isn't it? Great. So with 4 workers, I got almost a 4 times speed up, a little less because of the overhead. And depending on the number of workers you have, depending on the size of problem, the type of problem, your speed up may vary. But the point here is just by adding PAR, just by adding 3 variables, 3 letters in front of my for loop, I was able to change the way MATLAB was treating this for loop. I was able to do that because my for loop, everything inside my for loop was independent of each other. If that weren't the case, MATLAB would have warned me. MATLAB will give me an error, and the code analyzer will help me to figure out what's going wrong. So that's parallel computing, and that's how simple it is to use par for loops instead of for loops. Now, another way of using parallel computing is to use GPUs. So if you have a multi-core CPU, multiple processors, parallel computing toolbox enables you to use all of those, but it also enables you to communicate with GPU cores and make use of GPUs. For those of us who don't understand GPUs, let me step back a little and talk about what graphics processing units are. So a GPU or a graphics processing unit is a collection, a massive collection of a lot of parallelly operating integer and floating point processors. It's really good at doing calculations which were originally intended for graphics, but it turns out they are similar to the calculations you do in the scientific world, in the engineering world. So these are very good in matrix operations, in calculations such as FFTs and transforms, and they have a dedicated high-speed memory. So GPUs are being used for scientific computation also. And MATLAB supports NVIDIA GPUs of compute capability 2.0 or higher. And you can visit this link to figure out if your GPU is supported. So let us see how you can use GPUs in MATLAB. Let me close all this and okay. So how do we use GPUs in MATLAB? If I run this app, I'll be able to show you. So what I'm trying to do is solve a second order wave equation. And I'm going to solve this using spectral methods, which means that I'll solve it using a lot of transforms and inverse transforms. And I'll solve it over different grid sizes, 2D grid sizes, and see how my CPU is able to handle it. So for a simple grid size of 64, let's see if I'm wanting to simulate 4000 steps, what is CPU doing? And you can see the CPU is able to calculate how the wave is propagating, and it takes some time to do that. But as the size of my grid increases, the number of calculations grows higher and higher, and it's not easy for a CPU to handle those calculations. So for example, if I have 512 by 512 grid size, forget about 4000 points. I cannot even calculate 100 points very easily. So let's stop at 100 steps and see how a CPU is able to handle these calculations. So the CPU is trying to simulate this second order wave equation using spectral methods, and it's moving a little and it almost reached 100 iterations. Great. It took 9.1 seconds to just calculate 100 iterations, and wave hasn't moved even a little in those 100 iterations. But if I make use of a GPU for that same calculation, for those same 100 iterations, let us see how fast a GPU can do that. And before I was able to complete my sentence, GPU has finished simulating, and I can see 0.9 seconds was the time taken by a GPU to calculate those 100 points to stop at that 100th iteration. So 0.9 seconds instead of 9.1 seconds. That is the difference in time when you're using CPU versus GPU. It's a good speed up, isn't it? It is. So how did I get that speed up? Let's go back to our code comparison tool and compare wave CPU and wave GPU, these two files. These are the files that are being called under the hood in that app. And if I compare these selected files, I can see most of the lines are almost same. All my calculation lines are same. What has changed is, if I scroll up all the way to top, I have added this line x equals GPU array of x, and similarly dt equals GPU array of t, dt, and so on. So to use GPU arrays, it is slightly different than using parallel for loops. Here you have to use two functions called GPU array and gather to send data to GPU arrays and get data back from GPU arrays. So by using x equals GPU array of x, I'm telling MATLAB that send whatever value of x is there onto the GPU, and now on whatever calculations I'm doing on x, use GPU to do those calculations, not my CPU. And then once I'm done doing all those calculations, so all my calculations remain the same, all my FFT, IFFT calculation, my real calculation, addition, subtraction, everything remains the same. What I need to change is when I'm updating my app, instead of passing in just XX, I have to gather XX back from my GPU and put it onto my app. Similarly, my value of VV has to be gathered. So I have to use GPU array and gather, these two functions, and everything else remains the same. The reason that remains the same is because all these functions, FFT, real, and so on, have been implemented to work on GPUs as well. So to figure out what are the built-in functions that are available on GPUs, I can do a doc search of the keyword GPU capabilities, and it will lead me to a page where I can learn about GPU computing. I can see GPU array and gather functions here, how to use them, some other GPU related functions. But the page that I'm interested in, if I scroll down, is an example in how to about running built-in functions on a GPU. So if I click on this, it gives me a list of MATLAB built-in functions that accept GPU array as input argument. These are all built-in functions, and this list is growing from each release to release. So if your function, if your implementation, if your algorithm uses only these functions, just by using GPU array and gather, you will be able to exploit the compute power of your GPU. Okay, so we saw that the speed up was almost 10 times for the size of array that we looked at. But based on what problem you're solving, what is the grid size, the speed up will differ. And you can see initially CPUs are faster than GPUs if the grid size is too small in this benchmark. But as the grid size increases, GPUs became faster and faster, and that's because the overhead is being taken care of. So you have once the overhead of sending data to the GPU, but then more and more calculations you can do on GPU before you gather, the better performance you will get. And if you don't have the supported functions, if you don't have functions, the built-in functions that you want which support GPU, you can always write your own custom functions which run on GPUs. Or in fact, you can import your CUDA or PTX kernels to run from MATLAB. So based on what level of control you want and what ease of use you want, you can select any of these options for targeting GPUs in MATLAB. So we looked at parallel computing, and we can conclude that it enables us to speed up our computations by allowing us either to work with GPUs or multiple cores or processors in my CPU. It gives me this larger compute pool. What it also gives me is a larger memory pool. So each of these MATLAB workers can have their own memory, can have their own resources, and you can distribute a large data set among these workers to work upon. Well, our focus today was on speeding up computations. So we talked a lot about parallel computing and how you can speed up computations. But I just wanted to let you guys know that parallel computing can also help you in working with large data as well. So let us summarize the whole session. Let us see what all we talked about. So one of the things that we talked about was how you can use pre-allocation and vectorization to make best use of matrix operations in MATLAB. What are the give and takes there, and what are different techniques that you can use. We then saw how you can use MATLAB Profiler to find bottlenecks and then use those techniques on those bottlenecks to focus your efforts to get the best results. And once you are done optimizing your serial code, we saw how Parallel Computing Toolbox enables you to use CPUs and GPUs and multiple cores to take advantage of additional computing resources that you have. Here are some other resources of recorded webinars available on our website and some blogs that you can refer to learn more about performance in MATLAB. Thank you for attending this webinar today.